Oh my gosh. Hi. Why is the quality so bad? I don't even know. Anyways. Hi everyone. Meaning me. Today we have a chem date. I don't know if you can see what I wrote on the board. We have a chemistry date and it's gonna last probably 2 hours. But I'm just gonna start off by saying um my chemistry exam's tomorrow. And I'm not gonna get any sleep tonight because I have not done any streams at all this entire semester about chemistry. And so today I'm going to compensate by going through all 4 chapters of the exam. And I'm gonna add a little fun twist to it because guess what? We're having a date today. Yeah, absolutely. We're having a date, and guess what? We're drinking wine. I'm just kidding. We're not drinking wine. This is cranberry juice, but it's like my little mixture concoction. So some people be like, ugh. Here, I'll explain later. But I'll show you how I make my concoction, okay? So you put cranberry juice in there. So it kind of looks like wine, but cranberry juice is good for you. But I don't like just cranberry juice. It kind of tastes nasty by itself. Well, I don't know. But if you add some Sanpel in there, well, it's not too much sparkling anymore, but if you add some Sanpel in there and you kind of mix it up, it makes sparkling juice, which is pretty cool. And it tastes nice. It's almost like wine, basically. It's like Moscato, But yeah, it's healthy Moscato. So if anybody's like, okay, you could have been drinking soda and you decided to drink some nasty carbonated juice water. Well, guess what? Soda does not have a nutritional value, and I'm a nutrition major, and I might as well put you on some healthy wine or healthy soda, and that's this right here. Anyways, we're also gonna be doing a tiny little mukbang. I have brought a lot of food from my restaurant. And so we got our garlic butter rolls, and then I have a carbonara alfredo. And then I also have meatballs. So yeah, we're gonna be eating for I think our first time today actually. Let me think. I don't think so. Did I eat today? I think I ate just a small bagel, but that's it. But yes, we're gonna be eating. This is bus. Basically, this is just me eating on camera until I finish eating and start owning up to the 4 chapters I have to discuss. I feel like this is awkward. I feel like the first date isn't going too well. I should probably say some things about myself. I've been super busy, but just now I got to everything. And so I can finally, talk and stuff and do work and stuff. These rules, by the way, are the best thing to happen to anybody on earth. Unless they don't like garlic. because this butter tastes like garlic, and there's actual like garlic particles in there. This is awkward. Let me go put on a video.
As I'm in the midst of applying for this. I felt like skipping the dramatic, philosophical introduction to this video. Let's get straight to the point. Given that it's the month of October, and given that I'm on an endless pursuit of the profound, I thought it might be a worthwhile challenge to figure out which horror movie had the most profound ending ever. Note that I did not say the greatest horror movie ending, because there's too many of those to choose from. And horror is too subjective a genre for there to ever be a firm consensus. When I say profound, I refer to anything that demonstrates depth, great knowledge, or insight. While horror doesn't usually cross into this territory, there are horror movies that compel reflection just as much as they compel feelings of disturbance. This can be key to a film's lasting success. If something about a horror film inspires deep thought, the audience member will have to keep thinking about the movie and, by proxy, re-traumatize themselves with all the disturbing things they saw. This is why the ending for The Shining is an automatic candidate. We're still talking about what happened at the end of that movie 4 decades later. There's the ending of American Psycho, The Lighthouse, one or two of David Lynch's movies, all profound in their own right. But which is the most profound? It took me longer than I thought it would to pick my nominee. This is because the film I eventually chose was blocked out of my memory for most of the deliberation on account of its unconscionable content. But when I remembered it, I realized there was no other possible choice. If you're a horror fan, you have almost certainly heard of the film Martyrs. This is because it has a reputation for being the most violent, sickening horror movie you might ever watch. And it is due to this reputation
Moving
that
on
most
to
of
the
you
carbonara.
probably haven't watched it. Admittedly, I avoided it for the longest time due to this reason. And I can confirm, with maybe one or two exceptions, that Martyrs might be the most violent, explicit, disquieting horror movie ever. It's so excessively violent that I can understand why so many critics thought it crossed the line from the artistic into the pointlessly obscene. Hell, I struggled editing this video together because there were so few clips that I could safely put in a video without risking demonetization. But ultimately, I disagree with those who say the film is pointlessly obscene, and it is mostly due to the film's ending. There is an unresolvable question that the audience is left with at the end of this movie. A question that brings out a philosophical impulse in every person who watches it. It is a question that is, in part, linked to the excessive violence and whether or not it had artistic merit, whether there was a point to it. The numinous nature of that question and the variety of philosophical interpretations it elicits motivates my belief that Martyrs might
I'll try to start by
have the
11:20,
most profound ending
maybe,
to any
hopefully.
horror movie ever. Today, I will explain the plot of Martyrs, particularly for those who do not have the stomach to watch the movie. Then I will attempt to do the impossible. I will attempt to give a definitive answer to that philosophical question. I will do this by drawing upon the words of the man who directed Martyrs, as well as honestly contend with other interpretations of the ending. If you have already seen Martyrs and don't want to hear the synopsis, please feel free to skip to this point in the video. The film mainly focuses on two characters, the first of which is a woman named Lucy. At a very young age, she was kidnapped by members of a secret society and tortured. Luckily for her, she was able to escape her imprisonment and found shelter at an orphanage. But unfortunately, she was stuck with lasting psychological damage. Unable to contend with the violence that was inflicted upon her, she spends the rest of her life searching for the people responsible for kidnapping her and torturing her. Towards the beginning of the film, she uncovers the identity of those who tortured her as a child, the Belfont family. She goes to their home and murders not only the perpetrators, but their children as well, hoping to find catharsis for the pain she had dealt with all her life. After she does this, she calls up her best friend Anna, a young woman that she first met when she found shelter at the aforementioned orphanage. When Anna arrives, she is horrified by the carnage that Lucy inflicted, but ultimately decides to help Lucy clean up the mess. Soon after Anna arrives, it becomes clear to Lucy that murdering the family did not bring her the resolution she desired. The pain of this is compounded when Anna reveals skepticism about Lucy's claims of childhood torture. All of this culminates in a psychological breakdown that leads Lucy to self-terminate. The next day, Anna discovers a secret passageway, which leads her to a prison which contains a brutalized, emaciated woman, proving that Lucy was right all along. Though Anna attempts to aid the woman, cleaning her and providing medical attention, this is all ultimately in vain, because soon after, a group of people arrive at the house, kill the woman, and capture Anna. The leader of this group, known literally as Mademoiselle, explains to Anna what is going on. She and the society she leads are attempting to discover the secrets of the afterlife through the creation of martyrs. The martyrs are typically young women who they torture to the point of death, but not so much that they actually die. The society's hope is that when these martyrs are on the brink of death, the martyr can catch a glimpse into the afterlife and relay what they see to their torturers. The rest of the film shows Anna suffering the worst imaginable forms of torture until she reaches that transcendent state. She gazes into the afterlife and relays what she saw to Mademoiselle. The society convenes to find out what Anna saw. While they wait for Mademoiselle's announcement, her assistant stands outside her door. She asks the assistant if he can imagine what comes after death. When he says no, Mademoiselle produces a pistol and tells the assistant to keep doubting. She then uses the pistol to self-terminate.
Verbo is for sharing all kinds of moments. From post-concert bliss.
The question that has puzzled me and so many viewers for over a decade is what Anna saw, and what about it made Mademoiselle want to self-terminate. There are as many attempted explanations for this question as there are interpretations of what actually happens after death, and with both, there is no canonical interpretation. That said, there is empirical information we can draw upon, information that might be able to steer us towards a closer approximation of the truth. And that comes from the one person who does know what Anna said, the writer and director of Martyrs, Pascal Laugier. Back around the time the film came out, Laugier did some interviews with people who asked him what the meaning of the film is. What was the purpose of the film's extreme violence? He gave a couple of interesting answers. First, the film is apparently a metaphor for what Laugier believes to be the decline of Western civilization. Quote, "I really believe that the Western world is sick. Martyrs is almost a work of prospective fiction that shows a dying world, almost like a pre-apocalypse. It's a world where evil triumphed a long time ago, where consciences have died out under the reign of money, and where people spend their time hurting one another. It's a metaphor, of course, but the film describes things that are not that far from what we're experiencing today. Moshe then goes on to say that while the extreme violence in the film is primarily a reflection of his view of the world's darkness, it is also a questioning. Quote, for me, the martyr represents the one who, having no other choice but to suffer, manages to do something with
Oh,
this
excuse
pain.
me.
Since we don't believe in anything, since the world is increasingly divided between winners and losers, what is left to the losers but to do something with their pain? Deep down, it's what the film is about. I believe the answer to the film's ultimate question lies hidden in these quotes. It seems to me that Lochier was trying to ask himself and the viewer what purpose there could be in these doomed scenarios. Could something good come out of a situation like Anna's? Imagine that you, like her, were locked away in an inescapable dungeon,
No,
doomed
Sam.
to suffer the worst forms of torture. Nobody would find her. Nobody would answer for her death. Can something be quote unquote done with the pain that Anna and Lucy experienced in these situations? If not, then what kind of world would allow for this pointless, cruel violence to happen? Phrased in a different context, if you believe in God, then what kind of God would allow this? Should we just bring about the apocalypse, to use Loget's word, in order to stop the misery? Granted, it's a very basic existential question, one that has been asked millions of times, but the original potency of that question is rediscovered through Martyrs via its brutal violence. Of course, that existential question has only two potential answers. There is either no ultimate transcendent meaning to the suffering of life, or there is. Let's start by saying, hypothetically, that there is no afterlife, and we apply this interpretation to martyrs. Many people believe that Mademoiselle self terminated because there was no afterlife, and thus no ultimate meaning to life's suffering, including the suffering that her society caused to people like Anna and Lucy. Therefore, she self terminated out of guilt and wanted to save people from that knowledge. This is a perfectly reasonable interpretation, one of the better ones. It does bring up some questions, though. First, the movie does imply that there is something, what with the beam of holy light that we see in Anna's eye. Now, there are neurotransmitters and endorphins that trigger in response to dying, which have been known to cause euphoric sensations and visions, such as looking through a tunnel, which is what Anna appears to see. Fine, maybe that chemical illusion played out, and when it was over, Anna saw that there was nothing after death. That's possible. But how would the society know that Anna's testimony was reliable? What if she lied? Given the empirically driven and morally bereft nature of Mademoiselle's society, I would think that they would have done repeated experiments to back up what Anna said. And even if the response was the same every time, I would think that the society would have prepared themselves to accept the truth long beforehand and build off of that knowledge. For these reasons, it makes no sense to me that Mademoiselle would self-terminate after just one completed experiment, nor does it make sense for her to do it out of guilt. If she did it out of guilt, wouldn't she have told the other members of the society to stop what they were doing before she died? While the interpretation of there not being an afterlife is reasonable, I think it makes more thematic, dramatic, and logical sense that Anna did witness the afterlife and extract the meaning of life therefrom. I say this particularly because knowing the true meaning of life would, I think, be something that would make Mademoiselle self terminate after one experiment. Why? I will begin my argument by returning to Mademoiselle's haunting final phrase, keep doubting. To me, this phrase implies that the whole point of life is to strive towards the ultimate meaning of life through a series of sufferings. If we discover that meaning beforehand, it renders the journey of life pointless. It's like if you were to learn about every aspect of a movie before actually watching it, what every shot looked like, what everybody said, what the musical cues were. What's the point in watching the movie after that? It is the doubt of what will happen that fuels the purpose of the journey. In Mademoiselle's case, it seems that by knowing the ultimate meaning of life, that fuel, that doubt, was eviscerated. Thus, her life was paradoxically rendered meaningless. She needed to self terminate because there was nothing left to strive for. She reached the top of the mountain. There was nowhere left to go but back to nothingness. If she communicated what Anna told her to the society, and that knowledge got out to the rest of the world, then the rest of the world would complete its deathly march towards the apocalypse, to paraphrase Logier. Perversely, yet poetically, Mademoiselle becomes a martyr in favor of life, because it would be better to doubt and keep on living than to remove all doubt and necessitate death. The most important reason that I hold to this interpretation is because it lines up best with Logier's statements regarding what the film is actually about. It would mean that Anna actually did something with her pain, that there was a point to all the suffering. She, like Mademoiselle after her, became a martyr for life and against death. The knowledge she gleaned from the afterlife turned her from the helpless victim in the worst imaginable circumstance into the greatest hero. That knowledge defeated the unconscionable evil of Mademoiselle and the society. Now, some might say, well, we don't know that. Maybe the society would just continue their efforts. Maybe, but if they did, whoever replaced Mademoiselle would find themselves in the same situation, asking themselves the same question. Do they choose to perpetuate that knowledge and bring about the apocalypse? Or do they choose doubt and thus life? Do you think you have a better interpretation?
Slay, that was definitely food for thought. Well, you know what? I've already had my food for my belly, so I'm gonna give you some more food for thought, okay? That's what we're gonna do. You thought I was playing? I was not. I was not about to play around with you. First off, I'm gonna read from the 3rd chapter, the basically substitution and elimination analysis, and how you can predict the mechanisms and whatnot. So basically, to predict the products, you have to determine the reagent's function. So there's nucleophilicity, which is determined by polarizability and high electron density. And then there's also basicity, which is for elimination reactions. So this is like strong base equals an unstable one, and it results in a weak conjugate acid. So if you have a reagent that is a strong base and a weak nucleophile, for example, DBN or DBU, it will result in an elimination reaction. If you have a strong base, strong nucleophile, for example, hydroxide anion, MEO anion, ETO anion, that will be SN2 and E2. And weak base, strong nucleophile, for example, halogen anions, RS IHS anion, RSH, and H2S, that's substitution. For a weak base, weak nucleophile, for example, water, MEOH, and ETOH, that will be SN1 and E1. Okay, so let me repeat that. Strong base, weak nucleophile, elimination. Strong base, strong nucleophile, SN2 and E2. Strong base, strong nucleophile is substitution. Weak base, weak nucleophile, SN1 and E1. A strong base is when weak nucleophile, examples DBN, DBU. Strong base, strong nucleophile, examples OH, MEO, ETO, all anions. Weak base, strong nucleophile, IBRCL anions, RSI, HS anions, SH and H2S. And a weak base, weak nucleophile is water, MEOH, and ETOH. So if two chemicals are listed on the arrow, then the the nucleophile or strong base is considered the reagent, and the other one is just considered the solvent. So the second thing you do is to determine the expected mechanisms by analyzing the substrate. So if it's a strong base, weak nucleophile, okay, so you're gonna analyze the substrate, okay? The substrate is the thing that's not on the arrow, and it's the thing that kind of like is the beginning of the reaction. And we're going to go through this with the primary, secondary, tertiary categorization. So for primary substrates, if it's a reaction with a strong base, weak nucleophile, that's going to be elimination. If it's going to be a strong base, strong nucleophile, it's going to be mostly SN2, but a little bit of E2. And if it's with a weak base, strong nucleophile, then it's SN2, and then it doesn't react with a weak base, weak nucleophile. For secondary substrates, for a strong base, weak nucleophile, it's E2. Strong base, strong nucleophile, that's mostly E2 and a little bit of SN2. For weak base, strong nucleophile, that's SN2. And again, just like the primary ones, it does not react with weak base, weak nucleophiles. For tertiary substrates, we got strong base, weak nucleophiles is E2. Strong base, strong nucleophiles, E2. Weak base, strong nucleophiles, SN1. And then weak base, weak nucleophile, half and half with SN1 and E1. So basically, for all areas, for all substrates, if it's a strong base, weak nucleophile, it's all E2s. If it's a strong base, strong nucleophile, it's more likely to happen that SN2 for primary substrates, and it is 100% E2 for tertiary. And then secondary is in the middle. For weak base, strong nucleophile, it is SN2 for the first two, for primary and secondary, but for tertiary is SN1. For weak base, weak nucleophile, it does not react with primary and secondary substrates, but for tertiary substrates, the reaction is 50-50 between SN1 and E1. Okay, and the third thing you're going to do is consider the regiochemical and stereochemical outcomes of each type of reaction. So basically this is going to help you decide the number of outcomes that like comes out. So basically the regiochemical and stereochemical outcomes are going to help you figure that out. So for SN2, so like dimolecular, I don't know how to say it, but anyways, you know what SN2 is. So the RC outcome is the nucleophile attacks the alpha position where the leaving group is located, and it replaces the leaving group with the inversion of configuration. This means that basically this is a molecule, right? This is the alpha position. Look, let's just pretend this is a molecule, alkyl halide, right? I have a ring on my ring finger. Or here, let's do this. I have a ring on my ring finger. The ring is the halogen. So that would mean this finger is in the alpha position, and these other fingers are in the beta position because it's connected to the alpha. But they're not the alpha because it's not connected to the halogen. So basically, there's a robber or whatever. He's a nucleophile. He's gonna attack my ring finger. He's gonna cut it off. He's gonna cut off the ring finger and replaces my ring finger with one of his fingers. So it's kind of like that. Like the nucleophile basically replaces the leaving group, and the configuration of the molecule is inverted. So for E2, usually the Zaitsev product is more preferred than the Hoffman, unless a sterically hindered base is used. Let me give you an example of a sterically hindered base. I don't. Okay, this is not fun. Enthalpy. Okay. I actually don't know. I probably will get onto it in a later section because I don't know where anything is. Anyways, so that's that. And do I have anything else to say? Oh yeah. And then the stereoselective trans outcome favored over the cis outcome, and there's a stereo-specific outcome, which means if it has a proton on the beta position, and the anti-periplanar position of the alkene is important. So, okay, move on to one reaction. So, if SN1, the nucleophile attacks the carbocation intermediate. So, that's the intermediate created by the leaving group. So, once the group leaves, it results in a carbocation intermediate, and the nucleophile attacks where that leaving group used to be. And so, it replaces that leaving group, and it gives a nearly racemic, I don't know how to pronounce that, mixture, and it's a slight preference of inversion of configuration to retention because of ion pairs. And for E1 reactions, it's always Zaitsev product over Hoffman, and then the outcome is stereoselective, and it favors trans disubstituted alkenes over cis disubstituted alkenes. So I will explain that in a bit. That's like towards the end of chapter 7, but right now we're going to start in chapter 4. This is going to be about alkanes, okay? So basically, alkanes are just straight up like hydrocarbons, no pi bonds at all. So propane, butane, pentane. So the system is called IUPAC, the system of naming these. So how you do this is first you name the longest chain of carbons. So if it's 1, it's methane. 2, it's ethane. 3 carbons, propane. 4, butane. 5, pentane. 6, hexane. Heptane. Octane. Nonane. Decane. You know. If there's a competition between 2 chains of equal length, you got to choose the one with more substituents, or like branches connected to the parent chain. And if it's arranged in a ring, you're going to put cyclo in front of it. So if it has 3 carbons and it's a triangle, it's called cyclopropane. And then the second step of naming it, you gotta list all the substituents branching from the parent chain. These are called alkyl groups. So basically, you're gonna count how many carbons there are. So if it's 1, it's methyl. If it's 2, it's ethyl. 3, propyl. 4, butyl, etc. Third, you're gonna number the carbons of the parent chain to locate the substituents, and these are called marking locants. So you're gonna make the first locant your lowest number. So you're gonna try to make all of the substituents have as low of a number as possible. So if it's like like this, right? You gotta substitute it here, here, here. You're not going to name this one carbon number 1 because that would make your first substituent carbon number 4, and you don't want that. So you're going to try to name this one number 1, this one number 2. So that one is considered the first. So basically what I just drew is 1, 2, 3, 4, 5, 6, 7. I have so first step you have 7 carbons. And then second, you got 3 subs. And I'm going to name these methyl because they have 1 carbon. 1 at the end. I got 3 methyls. And then the third step is I'm going to locate the substituent. So it's 2. There, I have 1 on 3, and I have 1 on 4, right? And then for the fourth step, you're just going to put it all together. You're going to organize the substituents based off of alphabetical order. So for example, let me just say that I have my third substituent as ethyl, right? So I have 3 subs, 2 methyl groups, and 1 ethyl, right? And the 2 methyl groups are on 2 and 3. The ethyl group is on 4 because that's 2. So what we're going to do is we're going to do 2, 3. You're going to group the... Oh, wait, I'm just kidding. You're going to do it in alphabetical order. So the ethyl group goes first because it starts with the E. So it'll be 4 ethyl 2, 3 dimethyl, because there's 2 of the methyl groups, dimethyl, and then you're going to go back to the 7 carbon atoms, and you're going to say dimethyl heptane. And it says ane because there's no double bonds. Pretend I put a double bond right here. You would do heptene. And if I put a triple bond right here, it'll be heptine. And let's say this was a ring. This was arranged in a 7 carbon ring. I would do 4 ethyl 2, 3 dimethyl cycloheptate. So basically that's how that works. And okay, let me explain how to name a bicyclic compound. So bicyclic compound just means there's 2 rings, because a bicycle has 2 wheels, right? So bicyclic compound is basically this. But there's a way of drawing them. So basically this is usually a common way of drawing these, right? And then there's this. That looks nasty. But so what this is called right here, it's called a bridgehead. It's the thing connecting the 2 rings together. So how are you gonna freaking name this? So this is what we're gonna do. First you kind of follow the general rules of whatever that is, but basically you have to kind of add a step where you count the paths it takes to go from one point. Like what are these points called? They're called bridgeheads. So there's 2 bridgeheads, right? You have to count the path. So the first path is to go up, right? So that's 1 carbon. And then from this path to this path, going to the right, there's 2 from here to here. Clockwise or counterclockwise, it's also 2. So that's 1, 2, 2, right? So what you would say in this case, you would call it bicyclo 1 dot, or is it 2, 2, 1? Yeah, because you do the largest one first. 2.2.1 in brackets heptane, because there's 1, 2, 3, 4, 5, 6, 7. So that's how you do it. Now, what if you had substituents on the bicyclo compound? Then you would try to count along the longest path possible. So, like here, here, to make the substituent as low as possible, basically. So yeah, that's kind of how it goes. I'm kind of like out of breath. Let's see. Organize substituents if it says it. Oh yeah, I already said that. Oh, if there's a complex substituent, for example, we have isopropyl and stuff. So basically, isopropyl is basically a let's say I have this, right? Boom, 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 boom. So on that second carbon, I have a group that looks like this. What would I even name that? Because it looks like a Y on top of the entire carbon atom. So basically, you're gonna treat it kind of like its own little parent group ish. A propyl group has 3 carbons. So as long as you count 3 carbons, it's like, yeah. So basically, you can do it either way. Either you're gonna memorize this Y looking thing as isopropyl, the common name for that, or you're gonna treat it as its own parent thing. So basically, you're gonna count 1, 2, 3. That's 3, but you're gonna treat it as its own parent. So you're gonna find the longest path possible, which is only 2 carbons. So 2 carbons makes ethyl. And so, here, give me a second. I don't know why that would be 1 methyl ethyl. I think this would just mean 2 methyl ethyl. Because it's on the second one. So basically, I think it's 2 methyl ethyl. So you would do 2 methyl ethyl. 1, 2, 3, 4, 5 pentane. Because, or you could just do 2 isopropyl pentane if you're gonna remember that. Anyways, so like 3 carbons is a propyl, but if it's branched, it can be called isopropyl. For butyl, that's 4. Sec-butyl is kind of looks like a little like ring. Isobutyl looks like a Y, but with another arm holding on to it. And then tert-butyl looks like a little broom. So, don't know if that helps, but it should. I want to talk about constitutional isomers. So basically, when you're drawing constitutional isomers of anything, you kind of gotta like make sure it's not the same chemical. So like, okay, let's do this. 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5. That's a hexane, right? So there's many different ways to draw like hexane. That's one of them. So that's one. This is another one. 1, 2, 3, 4, 5, 6. That's another way to draw a hexane. And then we got this. This is another way to draw a hexane. Another way to draw a hexane. Boom, boom. That's another way to draw a hexane. That's another way to draw a hexane. And if you can't tell which 2 are like the exact same, you gotta think. You gotta use IUPAC. So I can already tell you right here, these 2 are the same. I'm gonna tell you why in like 2 minutes. Okay, so how about we name this? So this is 1, 2, 3. Why is it like that? Okay, 4, 5. That's the longest. Oh wait, these are all pentanes, right? Sorry, I'm being dumb. 1, 2, 3, 4, 5. Well, that's not pentane. Whatever. Anyways, oh wait, never mind. Okay, I'm being dumb. All these have to have different names. Basically, you're gonna do C6H something, right? Okay, so basically there's 6 carbons, but they're gonna have different IUPAC names. So this one is obviously pentane. You're gonna see there's a methyl group right here on 3. 3-methyl pentane. Now what about this one? This one, you can't do this 1, 1, 2, 3, 4. That's too little. There's possible that you can do 1, 2, 3, 4, 5. So that's the longest chain you got right there. So that's a pentane. But oh, if you count 1, 2, 3, there's a methyl right there. So it's 3-methyl pentane. So basically, you can just leave one of these out because this is the same thing. So let's test it on here. This is hexane. So obviously it's not. So this 1, 2, 3, 4, 5. This is 1-methyl pentane. And then 1, 2, 3, 4. This is. Oh wait, that's not 1. That's 2. Sorry. This is 2, 3-dimethyl propane. This is 1, 2, 3, 4, 5 pentane. This is a 2,2-dimethyl pentane. So often you won't know if it's the same exact constitutional isomer unless you like name it out. And so it helps to know what you're doing so you can figure out if you can op on the screen or not, you know? Okay. So I'll pull out my review sheet so I can tell you what to do. Okay, so we already got that. Okay, so let's talk about stability of isomeric alkanes. So, I think we're gonna start talking about Newman projections just a little bit. So I will talk about Newman projections because I just today understood what Newman projections mean. So listen up. Okay. So let's say, okay, the first thing you need to know about Newman projections, first thing you need to know is that they're always, unless specified, it's always looking down the C2 and C3 bond. I'll explain that in just a little bit. I'm going to give you an example. So let's do this propane right here, but we're going to do some wedges. So obviously this wedge comes out, meaning it's coming out at you. So this is not going to make sense until I explain just a little bit. BR on a dash, CL right here, BR on a dash. All right. So we got 2,3-dibromo, 2,3-dichloropropane. So that's what it looks like. And basically how this molecule looks is that, pretend this is the carbon chain, right? This chlorine is connected like this, like it's 3D, right? So it's sticking out. The thing means it's sticking out at you. So this is literally that chlorine right here. There's 2 chlorines, so that chlorine's also sticking out, so it just looks like this, right? Coming out at you. These BRs are on dashes, which means it's coming back. like that. So if you're going to take this singular carbon, let's just look at the singular carbon. And this is my hand. This is that singular carbon. The Cl is sticking out. The Br is coming back. If you were to rotate it this way and look at it this way, it will look like a Y because this one used to be sticking out, this one used to be sticking back, and now you're rotating it, and now it goes left and right. So that's basically what you're doing in a Newman projection, except you're acting as if you were standing right here in front of that molecule, your eyeball right here. So this is considered C2, that's the second carbon. C3, you're looking down, and you're looking straight at that carbon, and you're viewing you this other carbon you can't really see because it's like right behind that carbon. But however, your perspective of it changes. You're not looking at it from the left or the right side. You're looking at it from an anatomical front anterior thing. You know, so like pretend this is me, that's the molecule. You're flipping it like face forward. So you can't see the back of my head. You used to be able to see the back of my head. Now you can't. But you can see more things that you couldn't see when you were like, well, you could see, but it's like you can see more clear, you know? So if you were to flip this molecule around, you're going to consider the other things that you see. So like, you see how this is going up? So first you're going to consider what you see right here. There's no line going up. There's only a wedge and a dash. So that's how you know it's going to be a Y right here, like that, right? Why? Because it's going to look like a Y. I already told you, you know, it's going to look like a little Y. So this is that middle of that carbon right here. And the second carbon is going to be behind there. So because you're looking down at like that. Cl is going out of the paper. So if you're going to flip it like this, Cl is going to be right here, right? Br is going to be right here. And what's going to be on the bottom? Well, it's not going to be hydrogen. Why? Because hydrogen is going to be elsewhere. But what you do know is you have a carbon right here, CH3. Right here. So you'll be seeing that CH3 on the bottom. So basically the Y I just did there is this part right here. See that Y? That wedge, that branch, and that part of the carbon chain? That Cl, Br, CH3. Yeah. And the reason Cl is not on the left is because this side is always going out of the paper. So basically, I mean, I could just switch it around, like CH3, Cl. This would be more accurate representation because this is coming out, this is going back, and then this is just going down. So that's that part. Okay, but what about the second part right here? What about the second part? Well, if you're going to consider that Cl that's coming back out, you're going to put it right here. In that second Br, it's right here. Well, what do you put in this up position? Well, of course, you have this thing right here, the other CH3. So you're going to put CH3. So that's how you draw a Newman projection for a molecule. Just looking at it, try imagine, it takes practice, but you're going to look at it from the side, basically. And look at it through the C2 and C3 carbon. And make sure you include every single part of the molecule. You know, like if this one branched out more, like if it was if this wedge was CH3, CH2, CH3, then this would be CH2, CH3. Like it would just keep going, you know? So that's how you're gonna include everything in there. So that's a Newman projection. Now we're gonna talk about the stability and energy conformations of a Newman projection. So basically, put this over. If it's the staggered form, meaning the form I just drew right here, so the boom boom, the peace sign, and equal amounts of space between each position, that's called a staggered form, is the lowest and most stable energy form. However, if it was a eclipse form, meaning they're close to each other, then it's highest in energy, and there's torsional strain put on that the molecule. So another thing you want to consider when you're talking about energy is, I think, steric interactions, like gauche interactions. So what are gauche interactions? Basically, like if like CH3, so usually you have like a typical Newton projection will have CH's and H's, right? Like a basic one. So it'll be like CH, H, H, CH. I'm sorry. H, CH, H, or whatever, like I don't know, it doesn't matter. Basically, the position of these CHs, if they're closer together, like CH, CH, this would be the highest form of energy, because not only is it eclipsed, but they're also right next to each other, which involves gauche interactions. So that's why it's like super high energy and least favored. However, if they're split out like this in a staggered form, but also they're not exhibiting gauche interactions because they're not close to each other, then that's the most favored form. However, there is a form where you could have like CH3, CH3. These two are very close together. They have gauche interactions, but it's not as bad as the eclipse form, So two CHs close together on a staggered form is higher than a staggered form without them close together, but not as high as eclipse form closer together. So yeah. Basically for cycloalkanes and their stability, the more angles they have, like the less torsional, like the less angle strain they have, the better. So for example, like cyclopropane, there's the torsional, or not, I keep saying torsional, the angle strain is very severe because it's, okay, ideally it's 109.5, right? But it looks like a triangle. It's obviously 60 degrees, right? So it's like it's really not stable. However, if a cycloalkane has like 12 sides, for example, it's less, it keeps getting less and less energy. Well, I will say it's like it gets larger energy, but it's less energy per carbon group, basically. But generally the trend is the more angles you have, like the bit larger angles you have, the more stable the cycloalkane. So about the conformations of cycloalkane, the half chair is the highest in energy, and then the boat second highest, the twist boat second highest, and then the chair is the lowest conformation. So yeah. Okay, so if we're going to talk about heat of combustion, a more branch group has less. It has less activation energy and heat of combustion because the surface area is a lot less. And then, okay, let's talk about some chair conformations and ring flips. So, this is gonna be kind of cray. So, this is a chair, right? Off rip, I'm just gonna be saying that each position on a chair conformations describe cyclohexanes for example, or not for example, by the way. So this is a chair, right? It looks nasty. Don't talk to me about it. So this is a chair. Each position on that chair is going to have an axial and equatorial position. So this is the up axial position, and then this is the down equatorial. Equatorial just means it's parallel to basically the structures, like the way its structure is going. Axial means there's an axis, like it's going horizontal. So each position has two. The reason why this goes up, because if it goes down, it just kind of looks ugly. So just go up, trust me. And then the reason why this goes down is because the chair was already going up, so you're just gonna go down. Basically follow the natural flow. So there's two positions. There's always an up and a down, and there's always an axial and equatorial. So it'll help you like decide what's happening. So yeah. Anyways, the axial for this one is down, and then the equatorial for this one's up. It kind of switches every single time you like. So this is up, down. So the axial one's up axial, down axial, up axial, down axial, up axial, down axial. Same thing for equatorial. This is down equatorial, up equatorial, down. I think this was also down. Or am I being dumb? Oh no, this is up. I just drew it wrong. Yeah. Anyways, you get what I mean. So that's a chair for you. So if you're going to perform a ring flip, I found a little trick for ring flips. Basically, if you're going to perform a ring flip, if the substituent is on a axial up position, you're just going to move it clockwise over here, and it'll go to an equatorial up, I think. Let me see how that works. Give me a second. Yeah. Basically, move it clockwise and keep it in the same position. So, like if this is down equatorial, you're gonna move it one position over, and it's gonna be down axial. You were to flip it again, it's down equatorial. Flip it again, it's down axial. And flip it over again, it's gonna be down equatorial, and it's gonna be down axial. So that's basically how it goes. That's pretty easy. So you're gonna note that the number of going over this again, heat of combustion is dependent on the number of atoms, branching, and steric interactions. Like if it's cis, then it's and eclipsed, it's like high. So for example, like if it's an alkene and there's a double bond and the substituents are both on the same side, it's a cis alkene. And the heat of combustion is much more than a trans alkane because the interactions, because they're close to the two substituents are closer to each other. If you're gonna decide on the stability of chair, the basically like any configuration is more stable the more equatorial positions it has, because the more axial position it has this thing called like 1-3 axial like interactions, and like that's not good. And okay, so we're gonna start talking about chirality and stuff. So let me sorry. Oh, am I late? I'm sorry. Oh, this is okay. I'm already done. Okay, this is chapter 5. Okay, we're getting to the good stuff. So this is we're gonna talk about stereoisomers now. Basically, okay, so isomers are same atoms, same molecular formula, different some other place. Constitutional isomers are they're similar in everything, but they differ in constitution, which is like the connectivity of atoms. Like, it's the CH2 is connected to the first carbon instead of the second one, etc., etc. And then stereoisomers are the same formula, same constitution, but different spatial arrangement. For example, it would be on a wedge instead of dash and stuff like that. So cis and trans is used to differentiate disubstituted cycloalkanes and alkenes, but not when substituents are in the same position. So, like, wait, sorry. I don't know what that means, but all I will say is, if it's on the same side, then it's cis, and it's on a different side, then it's trans. Like different side of the ring or different side of the double bond, you know? Okay, so basically there's more types of stereoisomers. There's cis and trans stereoisomers, but there's also chiral molecules. So chiral just means that they're mirror objects, and if there's non-superimposable, then it's called an enantiomer. So for example, my hands look similar, like if pretend there was a mirror in between both of my hands, obviously they're mirror images. However, if I were to move it like this, you can't put one of my hands on top of the other and like produce the same, same image. However, if you were to get a heart, for example, no, that's still not. If you get a circle, right? No, because then, am I being dumb? I'm sorry. Give me a second. I feel like something's not right. Oh, okay. So that's when it doesn't have like an internal thing. I'm like freaking out. Okay, never mind. Okay, I get it. Okay, so let's do a half heart, half circle, right? And then half heart, half circle. There's a plane of symmetry, like that. You see? But if you fold these two together, it won't fit because it's an external plane. But if it's an internal plane like this one, you could fold a heart in on itself. You could also fold a circle in on itself and basically have the same shape. So, like, it's called a meso compound, basically. Anyways, I think I'm getting a bit too ahead of myself. Basically, we're talking about chirality, and chirality just means that they're non-superimposable, and they have enantiomers. And a common sign of chirality, the most common sign of looking at chirality is if it has 4 different groups connected to it. So for example, like a hydrogen, a hydroxide, and then 2 different sides of the carbon molecule. So to assign configuration to a chiral carbon, a chiral center. So for example, let's just say this one is connected to OH, but also connected to Br, right? Actually, let's just do it's connected to Br. So is this a chiral center or not? Yes, it is. Why? Because look, it has technically a methyl connected to it, and then an ethyl connected to it, and then a Br, and then you can't see it, but it's a hydrogen. So that's 4 different groups. So how am I going to determine whether this is R or S? So basically, you're going to determine R or S based off of the chiral center. So basically, R is clockwise, and then S is counter. Okay, how are you going to prioritize these? So the highest atomic number is always the highest priority. So automatically we're going to give Br the boot because the atomic number is 35. So that's number 1, right? And then hydrogen, let's just say hydrogen's right here, right? Hydrogen, we're gonna give this a 4 because we know hydrogen is number 1, and that's not a high number. And then these two that are connected, these two types of carbons, these are gonna be 2 and 3. We just don't know which ones yet. So they're tied because this one's a C, right? And then this one's also a C. How are you gonna decide whether this or this one is more priority? Well, keep moving. The C is connected to a C. This C is connected to 3 H's. So this C is going to be more prioritized because it's connected to a C, and that C is higher than that H. So this one's going to be 2, and this one's going to be 3. Okay, well, what if this C had a double bond to C, and this one was connected to C? Sorry. And this one's also connected to H and H. Well, if you're going to look at it from that point of view, double bond, it just means this C is connected to a C and also another C. It kind of just is like pretend a double bond is 2 C's. So this carbon is going to be connected to a C and an H. So it still loses because this one has a double bond and it's CC. So like move down the list, C, C, this one's CH. It still loses, So it goes 1, 2, 3, 4. So let's just not care about the 4. We're going to assign configuration off of 1, 2, and 3. So is it going to move clockwise or counterclockwise? Let's connect them. 1, moving around the chiral center. 2, 3. That's moving clockwise. So we're going to assign this one R configuration because R is for clockwise. And again, if it was counterclockwise, it would just be S. And then enantiomers are optically active. I think I don't know how to say this, but okay, so enantiomers, they rotate plane polarized light. You don't have to worry about what that is, but basically just know that they like 2 enantiomers, they'll rotate the plane polarized light in equal amounts in opposite directions. So if a reaction or solution has only 1 enantiomer and there's no other enantiomer, it means it's optically and enantiomerally pure and it's optically active, like it can move light. But a solution with equal parts of both enantiomers is called a racemic mixture, and it's optically inactive. Why? Because, well, one is moving the light this way, and one is moving the light this way, so it'll cancel each other out, and so, there's no movement. There's no net movement, But a solution with unequal amounts is it is said to be an enantiomeric excess, or EE, and it's optically active in whatever position the predominant enantiomer is in. So you just subtract. If you to figure out what enantiomeric excess is, just subtract the smaller percentage from the larger percentage, and just yeah. So okay, if you're gonna figure out what the number of stereoisomers possible, to count how many chiral centers, and then do 2 to the power of n, and where n is the number of chiral centers. And then let's see. We are going to fusion has only one enantiomer. Okay, yeah. Okay, diastereomers are not mirror images and have different physical properties. So basically, cis trans stereoisomers are diastereomers because they're just very different. So for a compound with multiple chiral centers, for example, 2, each one can have an R or S configuration, and this gives rise to 4 stereoisomers. So 2 pairs of enantiomers and 2 pairs of diastereomers. A compound with a single chiral center is chiral, but not necessarily with 2 chiral centers. So let's just, basically I'm trying to say, okay, well, remember I said to talk about the plane of symmetry, like on the outside? That's called rotational symmetry. That doesn't matter. Like, those are just, like, I guess, those are enantiomers, and, like, they're chiral. But if a molecule that has a plane of symmetry within itself, like a heart, for example, heart shape, it has reflectional symmetry, and any compound with reflectional symmetry is achiral. So, yeah. So there's something called mesocompounds, and basically these are compounds with chiral centers, but they're just they're achiral because they have reflectional symmetry. And a mesocompound will always have less than 2 stereoisomers. But yeah, Fischer projections, what you need to know about them is the horizontal lines are wedges and the vertical lines are dashes. They represent that. And then let's see. Longest freaking stream in 1 hour. It is 12. The presence of a chiral center is not necessarily a condition for a compound to be chiral. Atrop isomers are stereoisomers that result from a hindered rotation of a single bond. This is commonly seen in substituted biphenyls locked into one of 2 conformations and cannot adopt a fully planar. Enantiomers have the same physical properties. No traditional separation techniques do not work. Okay, so enantiomers cannot be separated traditionally, but diastereomers can. Alright, so for cis and trans stereoisomers, that's talking about like alkenes, but like for disubstituted. So like if like two of them are one side or both of them are on the other side. If it's tri or tetrasubstituted alkenes, we use Z and E. And so like the Z is like highest priority group on the same side. So like the two big groups are on the same side of the double bond. And if they're opposite, then it's E. So technically trans is E and then cis is Z. I'm gonna talk about 6, as in chapter 6. So we'll talk a little bit about enthalpy. So when electrons bond, they occupy a lower energy molecular orbital. What? Nah, bro. I don't like the way the stream is going. I'm going to, since it is almost 1, and I don't have a lot of time, I'm going to go back and highlight everything I need to highlight, and then go do like a quick stream, probably, and then we can do an anatomy stream, because since I have to do that, and then I will probably do some chemistry practice questions and sleep and stuff, because I need sleep probably. But yeah, thanks for joining me. I had fun talking about the first 2 chapters. I need to start talking about the second 2, but I kind of got lost. So I'm gonna start highlighting like the important things I need to mention, and then figure out from there. But yeah, I will go do that right now.